Good morning. How is everyone? Let's start off with prayer and then we will jump into our finishing up the learning checks for chapter 13. Dear God, thank you for this day and thank you for another week. I thank you that we are into the month of March, Lord. I pray that you would bless this month, help all the students with everything that they have on their plate for this month. I pray that you would help them with their stress levels and anxiety, help calm all their fears, Lord, and be with them. Help them to learn and grow and just do everything that's set before them, but most of all, help them to learn how to be still and know that you are God, Lord. So we thank you that you are God and that you are good. We praise you for that. We pray that you'll bless our week. Pray this in Jesus' name. Amen. All right. So let's see here. Your grades are up on Blackboard. You'll get back your learning assessment on Wednesday, Thursday. Still don't speak to anyone about it because there are still a couple more people who need to do the learning assessment. Um, just full disclosure, there's a different curve for the learning assessment for the Wednesday people than the Thursday people. It's only slight, but there's a different curve for the Wednesday versus Thursday because Wednesday will always have to do their learning assessments first. So they always have one fewer day than the Thursday people to study for it. So they will always get a little bit more. It's not a lot, it's just a couple, 2, 3 points, but it's still a little bit more just to say like, okay, you guys have a little bit more stress on you than the Thursday people. But anyway, so you'll all receive that back this week. Please go through and correct everything on your learning assessment and on your exam so you can see your Blackboard exam. You can see what you got wrong. So the same way that you see your problem sets, look back at those to correct those. Look back at your exam to correct all of that. All right. Any questions before? Oh, for lab this week, you just need what is listed in the syllabus. So just what you see there. It's not the same. We're not doing a reaction. We're doing a bunch of mini reactions to figure out what your unknown is, but there's no mechanism. There's no overall reaction to write for this week. So just follow what is listed in the syllabus. All right. Any questions before we begin? All right, so our next reaction sequence, we start off with an alkene, we add in bromine and our solvent, right? This carbon tetrachloride, this is our solvent. And so we know that's not going to react, right? The only thing that's going to react is the bromine, and we know that that's going to react in an anti-addition. So if that's in an anti-addition, then really what we're going to see are these two bromines that are added anti to one another. And we know we would go through a bromonium ion. So here's a bromonium ion, one of the examples of the bromonium ions that we could draw, where we keep the ring atoms in the plane. Because this is an acyclic alkene, we're going to show the stereochemistry, this trans stereochemistry, right? This is trans. So we want to show that here in our product. So I'm going to do both of those isopropyls down, not one up, one down, but one in the front, one in the back. That's how we show that they're trans. Not up, down now, just both of them down because the bromine's at the top, but they are trans to one another. So if this is our intermediate, we know that this would be our product where we would still have one of these down and still as a wedge, but now the one that was down and as a dash now is pushed up. So this would be our intermediate. And no, we haven't drawn everything in the plane. The last thing would be to rotate so that we get all those carbons in the plane. But that's last chapter stuff. We don't have to mess around with that. Just remember how we did that. And also remember here that if I have an isopropyl down here that's on a wedge, then that means I have a hydrogen down here on the dash. If I have an isopropyl up here that's on the dash, then that means there's also a hydrogen there that's on the wedge. And both of these are acidic because they are one carbon away from a leaving group. So if we add in 2 equivalents of this base, sodium amide, then we can do our double elimination. Now we've seen this elimination, we've seen the double elimination. And so in this reaction, we're going to make, so let me number these carbons. And remember, you can number it however you want. This is arbitrary. So here are my atoms. Carbon 2, 3, 4, and 5 all have to be linear. I know I'm making the triple bond between 3 and 4 because those are the carbons with the leaving groups and the acidic protons. So I know I'm making it between 3 and 4. I know 3 is bonded to 5, or sorry, 3 is bonded to 2 and 4 is bonded to 5. And I know that 3 and 4 are both linear, so it has to be a straight line. So then what else do I have? Well, on carbon 2, I have carbon 1 and a methyl, and I have carbon 6 and a methyl on carbon 5. So that would be my product there. So I lost the hydrogen and the bromine, so I'll color code them. I lost this acidic proton and this bromine. It has to be rotated so they're anti to one another, but those two are the ones that are lost together. And then this acidic proton and bromine, those two are lost together in order to give us this product where we get an internal alkyne. So with our internal alkyne, how many equivalents of base did we need? We only needed 2 equivalents of base because it was an internal alkyne. If it was a terminal alkyne, we know we would need 3 equivalents because 1 equivalent would be used just to deprotonate that alkyne. But there is no alkynyl hydrogen here to deprotonate, so we only need 2 equivalents of the strong base. So then our last step here is a hydration. We have to have this Hg2+, this mercury ion here for the hydration. When we were doing the hydration of an alkene, all we needed was this stuff, right? H2SO4 and water. That's all we needed to do the hydration of an alkene. But now to do the hydration of an alkyne, we also need the mercury ion. So for this reaction, we're going to end up with this intermediate. So I'm going to draw the intermediate up here. And the intermediate we know is called an enol. We get an enol intermediate. Now, did it matter which carbon got the OH here? No, because they're both the same, right? Carbon 3 has an isopropyl, carbon 4 has an isopropyl. There's no difference in those two carbons. They both have the exact same thing on the other side, so it doesn't matter which carbon got the OH. But if those two carbons are different, then it does matter. But here the enol will tautomerize, where we will basically, let me draw this in. So let me give this a bond here. So we can go pick up this proton and then we move these electrons into this bond where we end up with this product where now we have a double bond where we had a single bond. And now we have a single bond where we had a double bond. We tautomerize it. So we know that that's not the cutest way of drawing it, right? So 1, 2, 3, 4, 5, 6. 1, 2, has a methyl, 3, 4, and then 5 has a methyl. So this would be a better way of drawing that product. So we said that is going to be the only product if we do this hydration of this specific alkyne. But what if we have this? If we have this alkyne, now the two sides of the alkyne are not the same, right? The two sides of that alkyne are not equivalent to each other. So HgSO4, H2SO4, and H2O. Well, if those two aren't the same, then we get this product. And this product, where carbon 2 gets the double bond to oxygen, the carbonyl, and carbon 3 gets it in the other case. We have two products that are possible there because we have the two sides of the alkyne as different. Here, for the example that we see, the main example on this slide, we only get one product there because we only have one kind of alkyne carbon. Questions on anything with this whole reaction sequence?
So just to clarify, what's happening between the intermediate with the bromine and the acidic hydrogens to the internal alkyne? So the acidic hydrogens are the ones making the double bonds or the triple bonds,
Right.
and
So
the
it's
bromines are
just the elimination. So we'll just say, okay, and there are two things here. And so we know base comes in, takes this proton, move these electrons, that leaves. So we end up with a double bond. And so if we had here a bromine and a hydrogen, then we would still have a bromine and a hydrogen in the end. And so then base comes in, move those electrons, and we'd end up with an alkyne. Double elimination.
Okay, thank
So
you.
we have one E2 and then a second E2. Other questions? All right. So now we have an internal alkyne. And we have H2 and Lindlar catalyst. So what does Lindlar catalyst do for us? Well, remember this is that cis hydrogenation, where our hydrogens are added syn. So we end up with a cis alkene in this hydrogenation. So 1, 2, 3, 4, 5, 6 carbons. Then we end up with this alkene. So we've added both of our hydrogens onto the same face. I don't have to show them, but I can draw them in. So we know there's a hydrogen here and there's a hydrogen here. They are added syn to one another. And so we end up with a cis alkene. So now with our cis alkene, we add in this alkenyl halide, specifically an alkenyl chloride, along with palladium acetate and triphenylphosphine. We are doing the Heck reaction. And so with the Heck reaction, you don't have to have the mechanism for this. You don't have to have the mechanism for the hydrogenation either. Just know that it's a syn addition. So we have carbon 6. We'll call this 7, 8, and 9. So 1, 2, 3, 4, 5, and 6. So which carbon's going to be bonded? Well, we're going to make a bond to either carbon 3 or carbon 4. It doesn't matter. They're the same. But we'll make a bond to one of those carbons to carbon 9. And then carbon 9 is going to continue to have a double bond between 9 and 8. So this is carbon 9. This is carbon 8. Now, what do we do with this 7-8 bond? Well, what was the stereochemistry to begin with? The stereochemistry to begin with here was cis. So we need to maintain that stereochemistry in the product that we draw. And so we still need to have cis stereochemistry. So what do I mean? What are cis? Well, this bond and this bond, those two are cis to each other. And we can see here, this bond and this bond are still cis to one another here in our product. So this would be our alkene product. We have made a diene here. Questions on this? All right, so I hope that you had already worked on these on your own, right? We said we were going to work on the learning checks ahead of time and then just check our work so that everything is a lot clearer to you. All right, here we have a terminal alkyne. I'm going to number it because we always want a number to keep track of all of our atoms. It's not the same as numbering it for naming it. All right, so we have a terminal alkyne and we add in 2 HBr. So when we add an acid here, this is going to be a Markov-Nikov addition. And so H goes where there are more H's. So where's the hydrogen going to go? Well, we know carbon 1 has 1 hydrogen, and we know carbon 2 has no hydrogens. So H goes where there are more H's. The hydrogen goes to carbon 1. And so if the hydrogen goes to carbon 1, we're going to end up with this product where it doesn't have to be linear anymore between 1 and 2. So 1, 2, 3, 4, 5, 6. And so on carbon 1, we've added hydrogens. We don't have to show anything, right? We know that just by looking at it, we can see that it went from having 1 hydrogen to having 3 hydrogens total. We added 2 hydrogens to it. And then carbon 2, we're going to add 2 bromines to that. So we end up with this geminal dihalide. So H goes where there are more H's. And so then the nucleophile and this nucleophilic strong acid goes to the other carbon of our triple bond. So this is kind of piggybacking off what we learned with the alkene. Now with the alkyne, we can add 2 of these to the triple bond. If we just added in 1, we'd end up with a mixture of products because it's difficult to add just 1 HBr to an alkyne. So we'd get the alkyne and we'd get this, we'd get the alkene where 1 has been added, and we'll get this product, this geminal dihalide. And so if we just add in 2, we can go all the way to the end. So look back at your notes. I said it's difficult to add 1 equivalent of this acid to the alkyne. You're going to get a mixture of products if it's a terminal alkyne. Questions on this one? All right. So now we have our NMR problem. So a lot to think about here for NMR problem. We want to use all the data. So the first piece of data that we have to use is this C5H6. So we need to do our degree of unsaturation calculation. So 2 times the number of carbons plus nitrogen minus hydrogen minus any halogens plus 2 all over 2. So 2 times 5 minus 6 plus 2 all over 2. So hopefully you can do that math yourself and you get 3. So 3 unsaturations somehow. So looking at the IR, let's see if those unsaturations come out, all or in part at least. So the IR, our first one is 1625. So we want to say what that is. So 1625, that's the carbon-carbon of the alkene. Then we have 2110. So 2110, that's the carbon-carbon of the alkyne. But typically, it is a terminal alkyne. You usually don't see this peak in this region if it's just a regular alkyne, internal. But if it's a terminal alkyne, you see this peak also, but this is referring to the stretch here between these two carbons. Just like this is between these two carbons, that's the stretch, the carbon-carbon stretch. Then we have 2980. So we know what that is. That's the alkane carbon-hydrogen. 3110, that's the alkene carbon-hydrogen. And then we have 3330, that's the alkyne carbon-hydrogen, which tells us it's a terminal alkyne. So what do we have here? We have an alkene and an alkyne. How many pi bonds does an alkene have? We know it's a sigma plus a pi. What about an alkyne? We know that's a sigma plus a pi plus a pi. How many pi bonds do we have here? 3 pi bonds, 3 unsaturations. Those are the 3 unsaturations. Remember, an unsaturation is a pi bond or a ring. We have 3 pi bonds. We have 1 alkyne and 1 alkene. So if you get 2 alkenes, you've got the wrong answer. If you get a triple bond and a ketone and an alkene, you've got the wrong answer because you can only have 3 unsaturations total. Questions so far? All right, then let's look at the proton NMR. So proton NMR, remember, we need to think about where the peaks are showing up. We know that there's no alcohol here, so we don't need to be looking at alcohol regions, but we know there's alkene. We know there's alkyne, CH of the alkyne, because it's a terminal alkyne. There might be something allylic, so right beside the alkene. The hydrogen's right beside the alkene, that's allylic. And then we also might have, just some regular primary, secondary, tertiary, very far upfield. All right, so let's look at our coupling constants also. In general, remember we ignore what's below this line. So we have things that have to do with alkenes, and then we also said we have this alkyne long-range coupling, which we don't ignore. So we have all these different things we need to be thinking about as we look at our proton NMR. All right, so our first one is 1.9 3H singlet. So 3H, it's integrating for 3 hydrogens. We need to label that as 1.9. How many more open spots does that have? 1. And it's a singlet, meaning that there's something here. So we'll just say it's a carbon that has no hydrogens on it. No hydrogens on it. All right, so then our next one is 2.8. So it's one hydrogen, so CH. I'll label this as 2.8. But that's kind of in a weird region, right? 2.8, let's look at our Proton Nmr data. So 2.8, that's not just a regular CH, right? That's too far downfield. So what could that be at 2.8? It's probably this in the Alkyne region. So that means this is probably triple bond to another carbon. Now, when we see that this is a singlet for the alkyne, we're not talking about here. We're not necessarily talking about right there. If we were talking about right there, that would just be this. These two are not coupled to each other. These two are equivalent to each other. So we're not talking about, there are never hydrogens here. We only have one more spot that's open. We can't fill that one open spot with a hydrogen. So there's never any hydrogens there on that carbon. So when we talk about it being, this could be a singlet, doublet, triplet, whatever. It's a singlet here though. What are we referring to? Well, let's look here. We're not referring to this carbon, right? This carbon has no hydrogens on it. We're referring to the carbon that is 3 carbons away. How many hydrogens are there? Do we have 1? Do we have 2, 3? Do we have none? How many hydrogens are over there? Well, this is a singlet, which means there are no hydrogens here either. We don't see any J value, which we should see. If there were hydrogens there, we'd see that J value. And we see that it's a singlet. If it was a doublet, there would be hydrogens there on that carbon. But it's a singlet, no hydrogens there. So again, we'd have to see this long range coupling. We'd see this J value of somewhere between 2 and 4. We don't see that J value. And we see that this is a singlet. So if this is showing up as a singlet, then there is nothing over here. If that hydrogen, that green hydrogen, is showing up as a singlet, there are no blue hydrogens. If it's a doublet, then there's 1 blue. If it's a triplet, then there's 2. If it's a quartet, then there are 3 blue hydrogens. So that means there are no hydrogens there. This is 2.8, 1H singlet. We've shown everything we can for that building block piece. All right, now 4.7, 1 hydrogen. Now 4.7, again, this is downfield, so let's see what this would be. 4.7 is probably here, this terminal alkene. So we need to show that that is a hydrogen attached to a carbon that's involved in a double bond. So this is 4.7. 4.7, 1 hydrogen, and it's a doublet. And so with that, we get this J value, 2.1 hertz. So let's see what kind of J value that would be. Well, a J value of 2.1 hertz, it could be this long-range alkyne coupling, but we know that's not an alkyne hydrogen, right? It's not an alkyne hydrogen that we're talking about. We're talking about an alkene, so it has to be something in this table. And it can't be anything that we are ignoring. So it's probably this, 2.1 is probably this geminal, where pink is coupled to blue. So that means, what does geminal mean? Twins on the same carbon. So that means we have another hydrogen right here on the same exact carbon. And so with that, these two are coupled to each other, and that is that 2.1 hertz coupling.
Doesn't the 4.7 value integrate for only 1 though?
It integrates for 1. Those 2 hydrogens are different from each other. They have a different chemical environment. So yes, it integrates for 1. If these two, if it was just a regular CH2, then yeah, these two would be equivalent. But because they are on this carbon that is now sp2, now what's over here? Let's say this is the bromine over here versus this being a CH3. There's no way for this hydrogen to be close to this CH3. There's no way for this hydrogen to be close to this bromine. We can't rotate. We could rotate here. We have rotation here for this regular CH2 that's sp3 hybridized, but there's no rotation. Everything's locked into place. So this hydrogen is close to this CH3, whereas this is close to this bromine. They are different from each other. So we would say that these two hydrogens, even though they're on the same carbon, they are not going to integrate for 2H. They're not going to integrate for 2H. All right, so that's our 4.7. We've shown why it's 4.7 because it's attached to an alkene. We've shown that it's one single hydrogen. It's a doublet because it has one hydrogen neighbor. This is the neighbor. And we've shown why it's 2.1 hertz. We've shown everything we can there. Then we have 4.8. If we look ahead, 4.8 has that same J value, which means we can technically add on to this and just say, well, that's 4.8. Right? One hydrogen. It's a doublet, one hydrogen neighbor, which is 4.7, and they have the J value of 2.1 hertz. You're seeing it from one side, you're seeing it from the other side. So these two are terminal alkenyl hydrogens. All right, how many carbons total are we supposed to have? 5 total, but if we look here, we have 1, 2, 3, 4, 5, 6, 7 carbons that we've shown. But we only can have 5, which means there has to be overlap. For the hydrogens, we're good there. 3, 4, 5, 6. We have 6 hydrogens. We're fine there. But there has to be overlap with these carbons. So how can we piece this together? And remember, this is why we always want to show that there are these open spots. Now let me go back to 4.7 and 4.8. We know there are no hydrogens on this carbon. Why do we know there are no hydrogens on that carbon? Well, let's look at the J value. We have this geminal that we see, but if there was a hydrogen on the carbon right beside, we would see either a trans or a cis coupling, right? They would be in vicinity of one another. We don't see that. It's not a doublet of doublets. There are no hydrogens on the carbon right beside. So if there are no hydrogens there, we leave those as open spots. We know there are no hydrogens on these other carbons that I've pointed out. So how do we put this all together? What do we do to piece this all together? Well, when we piece this all together, we're going to end up with a CH3 with a single bond to a carbon that has a single bond to this carbon of this triple bond. Right? This is our 2.8, and this is our 1.9. Now we know that this carbon here in the middle has no hydrogens on it, and so that's probably the carbon that's in a double bond to the other carbon with 2 hydrogens on it. Where one of these, and it doesn't really matter which one, is 4.8, and one of these is 4.7. Here there's no like cis-trans stereochemistry, so there's no way for us to know. And actually a better way for me to draw this would be like this, where you can see that this is linear here. And then you got your 3 hydrogens, and you can see this is trigonal planar at these 2 carbons. And so you can see everything as it is. We know this and this, trigonal planar. We know this, tetrahedral, but there's no cis RS that we need to show, so we don't have to do wedge dash there. And we know this is linear. All right, so we've added in all of our hydrogens. Let's add in now our carbons. So here we have our carbon data. So CH3, that's probably going to be this one, which is 33. Because we know it's a CH3, it's the only CH3 we have. Then CH, we only have one CH, and that's going to be this, which is 80. Now let's look at this data for our alkyne, 65 to 95, our alkene, 100 to 160. 65 to 95 for our alkyne, which fits, we said that's 80. And then we have another quaternary carbon. So quaternary carbon, which one would this one be? Well, it's probably going to be 92. Then we have our higher value quaternary carbon, which is going to be this, 155, involved in this alkene. And then we have a CH2, 147. Now, even though both of those hydrogens are non-equivalent to each other in the proton NMR and carbon NMR, this carbon just says, I have two hydrogens on me. I don't know why they're different from each other, but I know I have two hydrogens on me. So it's just called a CH2. But in the proton NMR, those two hydrogens are non-equivalent to each other, so we get two different peaks for those. But this would be our final structure. We have assigned all the hydrogens, we've assigned all the carbons. Previously, we showed that J value. We can show it here, we don't have to, but I'll just show it here. That's the J equals 2.1 hertz. And then we had no J value for this because we had no way of coupling that because there were no hydrogens here. So we had no alkyne J value because we had no hydrogens 3 carbons away. But we've assigned every carbon, we've assigned every hydrogen. This is our final structure. Let's do the name of this really fast though also. So here we have an alkene and we have an alkyne. There's a tie. They're both on carbon 1, either direction we go. So we give our alkyne, our alkene the lowest number possible. So our alkene is attached to carbon 1. And so the name for this would be 2-methyl, 1-butene, 3-ine. This is an alkene-ine. Questions on any part of this NMR problem? All right, then. If there aren't any questions, then we will go on to our next. Oh,
Oh, just before that, we assign hydrogen. I just wanted to see that page real quick.
This?
Yeah. Hold on. So, thank you.
Mm-hmm. Got it? Okay. All right, then let's move on to chapter 14. So that means that we are done with 13. Problem set is going to be available for you later after we finish lecture, and it'll be due on Wednesday. So problem set due Wednesday for chapter 13. So now we're beginning chapter 14, where we talk about delocalized pi systems. So we know what pi bonds are. Double bonds have pi bonds, triple bonds have pi bonds. We're mostly just going to go back to talking about alkenes, but now we're going to have a lot of alkenes in a molecule. And so we'll see in this chapter that the ability of molecules to absorb light in different frequencies, this is a consequence a lot of times of the multiple double bonds. So this is beta carotene. It has all these double bonds here. And so with all these double bonds, this compound is why carrots look orange to us. Because of this compound in a carrot, beta carotene, this gives the carrots their orange color. It has 11 double bonds. And so it causes the absorption of visible light so that we can see that color as orange. So before we get into our delocalized pi systems, let's look at Proverbs 4. It says, get wisdom, get understanding. Wisdom is the principal thing, therefore get wisdom. And all you're getting, get understanding. Exalt her, wisdom is personified in Proverbs. Exalt her, and she will promote you. She will bring you honor when you embrace her, when you embrace wisdom. She'll place on your head an ornament of grace, a crown of glory she will deliver to you. So as you are studying God's creation, he's revealing to you who he is. And so as you figure out more about his creation, as you find more of this information, know that that should be giving you wisdom and understanding. So let that wisdom and understanding show you who God is as you are, going through all of your studies in the sciences. All right, so we're going to talk about this allylic system. So what did we say allylic was in the previous chapters? Well, remember from our, let's put one hydrogen here. From our chapter 12, we talked about this allylic carbon. And so this carbon or this hydrogen, we would say that they are allylic because they are right beside the double bond. Right beside the double bond, that carbon right beside the double bond, or the hydrogen or hydrogens on that carbon right beside the double bond, those are called allylic. So we're going to look at this allylic system and see that it has some pretty interesting characteristics. So 3 observations. Here's the first one. So observation 1. When we are looking at our bond association energies, remember, so we have here 101. So that's breaking this bond where we would end up with, so if we have this starting material, break this bond, 1 electron goes there, 1 electron goes to the hydrogen. What are we going to end up with? A primary radical and a hydrogen atom. Versus if we had this, break this bond, so the same bond breakage, but now we're going to end up with a tertiary radical and a hydrogen. So remember, we look at our bond association energies to see how easy it is. And so we said it's easier for us to break this bond. This is a weaker bond. It's easier for us to break it because we're going to make a more stable tertiary radical. This is very unstable, the primary radical, right? And so it's more difficult. This is a stronger bond when we're going to make a primary radical. So we already know about that, right? We already know about our radical stability. We said primary is our least stable, and then secondary, and then tertiary. And we also know, just something else to note here, that this is trigonal planar. That's why I'm drawing it like that. When we have our carbocation, when we have our radical, they're trigonal planar. So make sure you're drawing them 120 degrees for the bond angles. So we have something weird that happens here. If we do this same exact reaction, so I'm just redrawing what's directly above, just redrawing that. If we do this reaction here, we end up with this radical, which is what you see up here, along with hydrogen. Now this is an allylic radical. Now let's see what the energy is. This is the weakest. When we're breaking that bond, when it's an allylic hydrogen we're breaking off, that's the easiest to do. So that means that the allylic radical is more stable than the tertiary radical. Even though, look at the allylic radical. What does it look like? It looks exactly like, these 2 radicals look almost exactly the same, right? The only difference is there's a double bond there. But it's way easier for us to break that bond, that carbon-hydrogen bond, when we have a double bond 1 carbon away. So the CH bond of propene is much weaker than the CH bond of other hydrocarbons, including 2-methylpropane, which would be a tertiary CH, which we see down here. That should be more stable, the most stable, but actually this is our most stable of our radicals. Questions there? All right, so here's our second observation. So remember we talked about our SN1, SN2. So here we're talking really about doing an SN1 reaction. So if we're doing an SN1, what do we need? Well, we said if we were going to do an SN1, tried to have the leaving group leave, we would end up with this carbocation, right? A primary carbocation, which we know is very unstable. Very unstable. So we don't do this reaction. Instead, we would do an SN2. Because we don't want to make a primary carbocation. But if we had this instead, that leaves, then we could make a tertiary carbocation, which we know is stable, right? Stabilized by hyperconjugation. So we can do that. And then we add in any kind of nucleophile, comes in and attacks that. So here, look at what we're doing up above. We have this primary carbon. It's a primary carbon. We have our leaving group leave. Somehow this reaction happened, and we end up with what looks like a primary carbocation, just like what we had down below, but there's a double bond there. Somehow this double bond being there makes this stable. Makes this stable. This is very unstable, but this can form. And so then our poor nucleophile, we know the next step can come in, attack that carbocation. Here they are leaving out 2 steps, stepwise process to do this SN1, where we end up with this ether that we've added. And so end up with this product where you get that CH2, oxygen, and then a methoxy group. So you can do the SN1 with this reaction. And so for carbocation stability, here we know primary is our least stable, and then secondary. But it turns out that secondary is approximately equal to allylic, and then tertiary is still our most stable. So allylic and secondary, they are approximately equal to each other in stability for carbocations. Allylic is most stable for radical, but it is kind of intermediate stability for carbocation. We can easily do that though, just like we can do the reaction if we have a poor nucleophile with a secondary haloalkane. We know that we're going to go through the SN1 mechanism. Questions on that? All right, so then we have our third observation. So our third observation here, we're thinking about acidity. So if we have this structure, what is this? This is a regular alkane, right? And we know alkanes are not very acidic. Alkanes are not very acidic. So if we were going to do this reaction, we add in some kind of a base, we deprotonate to make here this carbocation. Well, we know that that's not very easy to do. We know that these are not very acidic. The pKa here is about 50. What do we want? Low pKa, right? Almost negative pKa's would be better. And so here, this is not very acidic, with this being an alkane. We have another alkane, so just again redrawing what you see below here. But with this reaction, now the pKa is approximately equal to 40. You can see that K is 10 to the negative 40. It's approximately equal to 40. So lower pKa, this means this is a little more acidic. It's still not acidic like H2SO4, but it's a little bit easier for us to make this because of this intermediate that we're going to make here. We're going to make this anion. So it's a little bit lower pKa, a little more acidic when we have this double bond right beside. Again, what's different here? There's nothing different with the carbon specifically that we're looking at, right? This carbon is the same. This carbon is the same for both. It's just this alkane carbon. But the difference is one carbon away, there's a double bond. So we have this really interesting thing happening with propene through these three observations. Questions on this? All right. So why are we seeing this difference in reactivity? Well, we're seeing this difference in reactivity because we have a reactive carbon center right beside a double bond. So what are the reactive carbon centers? Well, it would be a radical, a carbanion, or a carbocation, right? A negative charge, that's reactive. A positive charge, that's reactive. A radical, that's reactive. A reactive carbon center, so some kind of very reactive carbon, they're all unstable. It's more stable to have it neutral, no lone pair, sorry, not no lone pair, no extra electron, unpaired electron. They're all very reactive, but it's right beside the double bond. And so with these reactive carbon centers, they are stabilized by electron delocalization. What does that mean? They're stabilized by resonance. So resonance is going to lower the energy of that reactive species. We can delocalize electrons by resonance. So let's look at our resonance forms here then. Resonance is going to stabilize. What are the resonance forms? Well, if we have that radical, remember that the arrow here for moving one electron is this. So this is for radical reactions, whereas two electrons for ionic reactions, remember that's a double-headed arrow. But anyway, we have three arrows here for the radical. So one arrow from the unpaired electron into the middle, from the middle of the double bond into the middle of that bond, and then to one of the carbons, where we go from this to this. Now remember, we're not just flipping this. This isn't a pancake flip. This is carbon 1, this is carbon 1. This is carbon 2, this is carbon 2, this is carbon 3, this is carbon 3. We're not moving any of the atoms around. When we do resonance, we don't move atoms around. All we do is move around electrons for resonance. Remember, you need the brackets and you need the double-headed arrow in the middle to show that this is resonance. So we can do the same thing for our carbocation. Where would we draw our arrow? From the middle of the double bond into the bond between that carbon and the carbon with the lack of electron density. And then we have from our anion, we start our arrow where we have that excess electron density. So now we have a negative charge on the carbon. So we start our arrow there and move electrons over to one of those carbons of the alkene. So we have these three resonance forms, and so they're showing you the resonance hybrid here, where we are delocalizing that unpaired electron and that double bond, or delocalizing the lack of electron density and the double bond, or the negative charge on the double bond over those three atoms. So why do we see this? Well, we see this when we can look at the molecular orbitals to see this stability, to see why we have this stability. So when we're looking at this propene, so any of those, the propene radical, the propene carbocation, the propene carbanion, or just propene itself, we have these 3 carbons that all have p orbitals perpendicular to the molecular plane. So you can see the molecular plane here. We know that it's trigonal planar. So all of our carbon-hydrogen bonds, those are in the plane. This is in the plane, in the plane, in the plane. All of these bonds are in that yellow sheet, the plane. And then coming up and down from the plane, we have our p orbitals. And so those p orbitals are overlapping, allowing for pi bonds. As they overlap, we get those pi bonds, not face to face, but side to side overlap. That's where we get those pi bonds. So if we look at this, because we have these 3 orbitals that are close together where we can get this pi bond formed, that's going to allow for us to delocalize these electrons. They can jump from being between these 2 carbons, being between these 2 carbons. So instead of these 2 sharing electrons, then these 2 can share electrons to make another pi bond. We can easily pivot the electron density. So here we're looking at 3 atomic orbitals. So we have 3 of these carbon atoms, right? If we have propene, we know we have 1, 2, 3 carbon atoms. So each carbon atom brings its own atomic orbital. But when those 3 carbon atoms come together, we make 3 molecular orbitals. So we mix the 3 atomic orbitals and we get 3 molecular orbitals. Now the atomic orbitals, each carbon has a p orbital. And so with that p orbital, we're using that, mixing those to now make 3 molecular orbitals that are pi molecular orbitals. So we make these 3 molecular orbitals. One of them is called pi 1, and then another pi 2, and then another pi 3. With these 3, we get here a bonding molecular orbital, a non-bonding molecular orbital, and then antibonding. Remember, we don't want to put any electrons into antibonding. We can put electrons into non-bonding, that's totally fine, and we can put electrons into bonding. Again, totally fine. But if we put electrons into antibonding, we don't make a bond. We have no compound. So when we put together those 3 atomic orbitals, we have this non-bonding that's going to allow us to put some of those pi electrons in, which keeps us a little bit more stable. So first, let's look at how many pi electrons we have. So our first compound would be here, double bond, positive charge. How many pi electrons do we have there? 2. Then we look at, with the unpaired electron now, that unpaired electron counts. So how many pi electrons do we have here? Now we have 3. And then finally, what about if we have a negative charge? We have to have a lone pair there. So we count all of those together, we have 4 pi electrons. So if we have 2 pi electrons for our carbocation, and we put those into the molecular orbital, they both go into bonding. If we have 3, then you can see that one of those is non-bonding. What does that mean? Well, we have this radical, this unpaired electron that's not involved in a bond. 2 electrons are involved in a bond, and one of those is not. Again, for the carbanion, 2 of those electrons are involved in making a double bond, and 2 of those are non-bonding, meaning that they are the lone pair. They're not used to bond. So this would be how our molecular orbitals look. Again, nothing in the antibonding. Nothing in the antibonding. We are lowering the energy. Look at the energy of our atomic orbitals. versus the energy of our non-bonding, we are lowering the energy by putting 2 electrons each into the bonding molecular orbital, and then we don't have anything in our antibonding, so we've lowered the energy overall. All right, we'll continue with this on Wednesday. Make sure you do your problem set. You work on that together. And I will see you guys on Wednesday for lecture. You still have questions, you can hang out for a second. I'll be here for a couple minutes, but if not, I'll see you guys on Wednesday. Have a good day. Bye.
Thank you.
You're welcome. Any questions?
Yeah, I had a quick question. About like the first 5-ish slides, we're talking about propene, pretty much the whole time. I'm assuming that that applies to any terminal alkene, like it could be butene, you know.
We are going to, yeah, so it applies to any kind of an alkene, not even just terminal, any kind of an alkene. And so then we will apply it to other systems later. But yeah, we're just looking at the simplest system now as we learn the like what's happening, and then we will apply it to other things later.
Awesome, thanks.
Uh-huh. Other questions?
Dr. Navani, I had a question about the lab on Wednesday. Are
Yeah.
we following the book's directions exactly? Like, are we doing the ignition test or just like the solubility?
Yeah, you're not going to be doing the ignition test, but that's not something that you would necessarily know. So yeah, just follow the book's directions, and then I will give you more direction when you get in there.
Okay, thank you.
Uh-huh. This is a short report, so yes, you can miss lab this week. That'll be the one you drop. Other questions? All right, you guys, have a good day.